Today, I'll be kind of giving a little bit more, rather than, I would say it's sort of, rather than a tutorial, it's a little bit more of a survey of kind of what's been done in solid-state NMR, looking at organic semiconductors, and then a few, descriptions of what can be done with analyzing perovskite systems. I noticed um, like several reviews that have been posted, and I'll be sharing those links as well. So my lab kind of recently started getting into a little bit more of looking at like organic semiconductor systems, some systems of triplet state. We started looking at a little bit more at thin films with some collaborators at NYU, including tetrathiopulvalene systems, DPP. But I won't be necessarily talking about the latest data from our group today, but just kind of some background on like, what are the structural relevant motifs in these classes of systems that govern their function, and what kind of NMR tools can be used to study them, right? So, click, right. So I'll be talking about organic semiconductors and doped lead halide perovskites. And yeah, if anyone has questions, you guys are welcome to ask questions over the course of my talk here. So when we talk about organic semiconductors, one thing that really influences their function, right, is molecular packing and chain mobility, right? And so we're often working in this class of structures, we're working with semicrystalline to amorphous structures. So there's this really nice review that goes over some of the structures and dynamics of organic semiconductors and how solid-state NMR can be used to study them. So often crystalline components can be accessible by diffraction methods. So these are like longer range structural order. In a lot of the function of some of these systems, it actually is like lamellar structures that can still have quite high charge mobilities, comparable to that of crystalline systems. So in order to fully characterize systems that have both long range and short range order, right, we know that solid state NMR is one of the methods of choice, right? And so these kinds of systems sort of enclosed by this blue square, those accessible by solid state NMR. So it can often be challenging to characterize systems with varying amounts of disorder, but as we know, this is kind of where solid state NMR shines. There's another paper I would kind of like to call your attention to that covers structure and charge transport in organic semiconductors. And I'll show a couple of the figures from this paper today, where they show kind of like the different kinds of ordering that you would expect for some of the polymers, so polymeric organic semiconductor systems, and what are the contributors to charge mobility. For the case of doped lead halide perovskites, we know that things like defect incorporation can have significant effects on band structure, absorption behavior. Also, we use relaxation methods to study these kinds of systems. So nanoscale organization in these classes of systems can be studied with solid-state NMR, and they also greatly influence how these perovskites function in devices, right? And so with these kinds of systems, we're working with soft ionic solids, and often we can have semi-crystalline components when we have organic incorporants, right? And so this is kind of the classic perovskite structure. We have cation, and B can be lead, X could be, a halide in this case, right? And we could, in principle, incorporate different types of defects in these kinds of systems through changing sort of the synthesis procedures, right? And there are also a lot of inherent defects in these kinds of structures as well, that arise due to how these things are made, whether like solution processing or mechanosynthesis and that class of systems, right? So today I'm just going to give an overview of magnetic resonance methods and some limitations of those methods. And I'll be going through a couple case studies for looking at organic semiconductors. So sort of what is the, if there's a organic semiconductor you want to understand, for example, how would you approach it if you don't really know much about it, right? Using very accessible tools to someone, that's in academics, let's say. All right, so let's start with the organic semiconductors. Oh yeah, so just to kind of get everyone on the same page, I think like since it is kind of general magnetic resonance audience, right? Maybe the bulk of the audience when it comes to these is already quite well versed in solid state NMR, but right, as we move from liquid state to solid state NMR, we introduce orientation dependence, right? So we now introduce chemical shift anisotropy. So here we now have to consider the chemical shift tensor, right? The full chemical shift tensor. We can think about the local magnetic environment for a particular nucleus, right? And the projection of the different components of the chemical shift anisotropy tensor or chemical shielding, I guess, in the way that I've drawn this here, that projection onto the main magnetic field, right? And so then we can then also describe this in terms of the chemical shift. Right? We can have a distribution of chemical shifts when we have a lot of different orientations in a powder-like system, right? Where each of these shifts represents sort of the projection of the field on one of the principal axes. Right? And then if we have an ensemble, we then have a powder pattern. And so how do we recover narrow line widths in solids? Or if we look at the form of the chemical shift anisotropy, so these are terms that are averaged out in the case of a liquid, we see the following expression, right, where we have this 3 cosine squared theta minus 1 term. Same thing when we consider sort of like the dipolar interaction, right? That interaction can be averaged out to some extent in the liquid state, right? It can be depending sort of on the extent of mobility of that system, right? It sort of can be recovered in the case of gels, right? So anyway, in this case, when you have a little bit more, in the case of a solid, you have this dipolar interaction, also another 3 cosine squared theta minus 1 term. And also if we look at the first order quadrupolar terms, we also have this 3 cosine squared theta minus 1, right? So what should theta be to remove these interactions? I think you guys all maybe know the answer here, right? So we want to align our sample 54.74 degrees with respect to the field, and we want to spin along this axis so we get sort of an averaging out of this 3 cosine squared theta minus 1 term. We can recover the isotropic shift, right? So I just wanted to touch briefly again on, how fast do we need to spin? Because when we think about like organic semiconductors, we do have sort of a fairly strong coupling interactions between the hydrogen nuclei. So typically you want to at least spin on the order of 30 kilohertz if you're looking at hydrogen nuclei. Plus you'd want to have a good amount of decoupling, right? So this is just an example of the enhancement resolution you get moving from 15 kilohertz to 100 kilohertz MIS. All right, so now we have that out of the way. So let's talk a little bit more about structural motifs in organic semiconductors. So here I'm taking 3 different types of organic semiconductors, right? And we know that sort of the critical factors in terms of having a functional organic solar cell or organic semiconductor, right? We care about absorption, charge mobilities, charge carrier lifetime, and the density of states, right, across sort of the absorption band, right? And density of states can also play a role in charge mobilities and carrier lifetimes because it can introduce additional recombination pathways as well. So all of these things then can be connected to how these molecules are then ordered in a film, right? So as we showed earlier, right? So we have this semi-crystalline structure that can form in this class of systems. You can also have ordered aggregates and also sort of amorphous structures that form. And so in this paper that I think I'll show the reference, I guess, at the end. But one of the papers that I'd been reading in the past sort of discussed that in a lot of these cases, you don't actually ever form a pure crystalline phase because you have disorder along one of the different axes of your system. So for example, in the pi-pi stacking axis, there's always a certain degree of disorder that lead to this sort of semi-crystalline nature in this class of systems. So you could have semi-crystalline, ordered aggregates, amorphous systems. And so we have a lot of molecular order and disorder at different length scales. So if we look at the mobilities, charge mobilities within this set of systems, if we look at the amorphous case, purely amorphous case, we have actually fairly low charge mobilities, which is not that surprising, considering sort of how broad the density of states is in the case of any amorphous system. You can have a lot of modes of recombination, not really good pathways for charge mobility. If instead you look at the semi-crystalline and ordered aggregates, now you start getting like reasonably high mobilities, depending on, these are kind of like the systems that work the best are on the order of 1 centimeter squared per volt seconds. And this is for organic semiconductors, right? So then the question is, right, it seems like you don't need a long range order for high performance. And this was something that was puzzling for people for a while, but the reality is you can have hopping between kind of these islands of crystallinity via this sort of ordered domains coupling to another ordered domain nearby. So you get sort of transfer via the chain from these organic semiconductors. So there's sort of, yeah, so depending on kind of the spacing of these ordered aggregates, you can still achieve mobilities that are on the same order as quite crystalline systems in this class of materials, right? So the relevant structural motifs that we care about backbone conformation, pi-pi stacking, locally ordered pi aggregates. This is kind of this, I don't know if people can see my mouse, but I think so. And also, right, the mobility and ordering of these alkyl chains, right? That'll also kind of determine how amorphous the system becomes. Right, so we, using salt-say NMR, we want to set constraints on distances, right? So we can understand how these systems are ordered. So, right, if we have a class of different organic semiconductor materials, we want to maybe assess, right, well, how much amorphous component do I have relative to the crystalline component or more ordered component that can give me some insight on how well the system is going to work in a device, right? So once again, we're looking at coupling of these of nuclei, so local atomic sites within these materials with a magnetic field. So we can look at the effect of local electron electron density and the different components of these molecules. We can look at the coupling between them to assess distances, either intramolecular or intermolecular stacking in these cases. And right, we can also look at the interaction with the local electron cloud, which is what I had mentioned already. And so in this, let's see, I think which paper is it? Yeah. In this Nature Materials paper, it's where they talk a little bit more about some of these semi-crystalline ordered aggregates and amorphous systems as when you're and comparing that to expected charge mobility. So I enjoyed that paper. Right, if you're looking for more advanced solid-state NMR of polymers, so a lot of the sort of workhorse NMR experiments, salt NMR experiments were developed quite a ways back. And if you want to learn more advanced NMR sequences, you can go through Schmidt, Rohr, and Spiess. They developed a lot of the techniques used in polymer physics NMR today. So, right. So what are the kind of experiments that are kind of like the workhorse experiments to study this class of systems, right? You can have your 1D, right, direct quantitative ratios of ordered and disordered components. You can do cross polarization, right, limited to nuclei that are in close proximity, right? So this can be on the order of 5 angstroms in inorganic systems. In 2D NMR, right, you also, head core is kind of also a workhorse. So all of these sort of HMQC type experiment, HSQC type experiments. This allows you to sort of scale contact times and sort of assess various distances between different nuclei in the system, right? And you can use sort of different types of recoupling, decoupling sequences to reach sort of more longer distances. Right, there's also homonuclear correlation, DQSQ correlation spectra, so you can get proton proximities as well. Multiple quantum MAS has also been used to look at sort of aluminum based like optoelectronic materials. I'll talk about one example today. And so this is, I think, it's quite a nice resource that discusses, right, angstroms and nanometers that are using sort of more advanced sequences to extend the distances that can be reached using in correlation experiments, as long as with a nice survey of the kind of methods that currently exist. So yeah, in addition, relaxation, right, is also a method that we use to study these kinds of materials. This is influenced by molecular motion, the dopants and paramagnetic species in your system, right? And introducing any additional spin active components in your system can influence the relaxation. And then also in each of the cases that I'll be talking about today, also their NMR crystallography has become somewhat critical in a lot of the papers that are out there today on organic semiconductors. So to be able to then run sort of a more straightforward 1D NMR experiment and then do a more complex sort of computational analysis to assess sort of ordered and disordered components. So yeah, so right now, a lot of the papers that are now published in this field, they incorporate molecular dynamics to produce model structures, right? You use DFT with the monomers using Gaussian, and then you can subsequently also obtain chemical shift calculations on monomers using Gaussian or CASTEP to look at more periodic materials or more extended materials rather. Okay, so let's talk about one case here. So the goal here I have is to characterize short range order in bulk versus film organic semiconductors with distinct backbone and side chain structures, right? And so here in the bottom left corners is from the Reddy group. This work that I'll be talking about today is from the Reddy group, at least in this section here. All right, so the question is, what is the contribution of ordered versus disordered components in 3 different OSC films, right? And how would I approach that, right? So I'm kind of asking, right, what's going on with like the ordered aggregates, mixture of ordered and disordered layers, right? Is pretty typical of OSC films. Okay, is everything, I think I heard something, but am I still connected?
Everything is good.
Okay.
Yeah, can hear you clearly. We can see your mouse cursor. So yeah.
Okay, yeah. So then, right, so then 1D NMR, right, short range order in polymeric organic semiconductors, right? So let's say I want to take this approach. I can look at, for example, in PTB7TH, I can look at the fluorine NMR, right? And I can assess, whether I have ordered or disordered components. And so this experiment was done at 30 kilohertz. And depending on whether I have sort of like narrower lines or broader lines, this might be some indication of whether or not I have some more ordered or disordered components. In this particular study, how are the distinct shifts justified, right? So often in these sort of complex structure motifs, you want to combine computation, right, with sort of more like 1D NMR data to really kind of interpret it to its full extent. So in this particular study, they do DFT of this PTB7TH system, just taking the monomer. And they change sort of the dihedral angles here in the CO alkyl group and assess to see, and then subsequently calculate the chemical shifts. And they see that, okay, depending on, how they organize the dihedral angles, they'll have a difference in the chemical shifts on the order of 24 ppm. And they use that as a means of sort of justifying that, okay, so if you then have sort of slightly less planars or more disordered system, on this section of the chain, then you have a significant shift, which can explain sort of the shifts that they see here, right? So you get this sort of larger twist in this kind of system and this large shift that they calculate, right? So these disordered chain structures, right, modeled using DFT, and they can justify these large chemical shift differences that are observed between ordered and disordered components, right? So that here, all I'm doing is kind of like the general approach of doing this sort of thing. So then they integrate and they get quantitative line shapes that yield the ordered and disordered percentages present in the film versus the case of the bulk. And so what they find is they get about 84% ordered in the powder versus something on the order of 99% ordered in the spin cast film, right? So this reference of NMR crystallography, Ashbrook, I think that's a very nice reference to kind of like give you an introduction on sort of these kinds of approaches that are now very widely applied in this class of systems. Right? So how does then this particular system compare to the MEH-PPV system that we introduced earlier? Right, so we can then now look at the carbon chemical shifts in this class of systems, and here we're spinning around 15 kilohertz, right? And so we can use cross-polarization, right? And this is mediated by the dipole interaction. It's sensitive to on the order of 5 angstroms, so less than 1 nanometer. And here they identify the following carbons as sort of backbone carbons, right? But once again, in this study, 1D NMR is paired with DFT calculations to once again support further interpretation. So this is kind of a common theme now in some of the more modern NMR papers that I've seen in this field, right? And here you can then take your monomers, sort of adjust the form of the chains, create sort of a distribution of dihedral angles, and calculate the chemical shifts, right? To give you some distribution in sort of the expected shifts for this particular backbone, right? So this is consistent with kind of what they would expect in terms of like the chemical shift range for sort of more ordered versus disordered components. And then you can then fit those components either using, use your favorite multi-peak fitting program, Origin, or let's say Topspin Solo, which is what they use in this study. Right? And so once again, with just 1D NMR combined with DFT studies, you can then start answering some questions about the degree of order and disorder in your film versus your powder, right? So here's something about on the order of 39% is what they determine and 43%. And so what they find is that MEH-PPV is more disordered in the backbone organization than PTB, and the films in general are more ordered for this class of systems in the way that they were made in this system. Okay, so what's another sort of useful thing to know in terms of like the 1D NMR analysis for this class of systems, right? So in this case, the goal now is to characterize, once again, the amounts of sort of ordered and disordered components, but specifically in this study, they're looking at crystalline, lamellar, and amorphous components in the film. So how would you approach this? So you have your sort of baseline monomer structure, and it's kind of sort of the same story in a lot of the cases that I'm presenting here. But sort of the first step here is to introduce the Gauss effect. If whether or not you've heard of this before, it's a recently well-known effect among people that look at polymer NMR, polymers in general. As we can use to, or just, yeah, I guess organic chemistry. Right? So the gamma gauche effect can be used to distinguish ordered and disordered chain components. So let's say we have like a long alkyl chain here, right? We can then sort of describe this alkyl chain in terms of the different carbons and also relative angles of carbons that are sort of 3 carbons away from one another. And whether you have sort of trans or gauche orientation, that will determine kind of where your chemical shift for that set of carbons appears, right? So if you have 2 methylene groups right here, that are 3 bonds away from each other, you can have either sort of this trans-trans configuration, which tends to yield higher frequency chemical shifts, right? So this is kind of based on sort of shielding and deshielding, as opposed to sort of a trans-gauche or gauche-gauche or trans-gauche. Yeah. Okay, so this is the angle that we're talking about, right? And so due to packing, trans-trans, it can be assigned to more ordered components, right? TG or GG to less ordered components. It's just related to kind of how the packing can occur, whether you have sort of a gauche-gauche or trans-gauche. So just using this description, so I would say, to kind of take this gauche effect as a, with caution, because it's not necessarily always true that it's going to be behaving this way. But from a 1D carbon NMR spectrum, we can then sort of see a sign, sort of, okay, so the sort of gauche, the trans oriented components, right, could assign this 33.15 ppm shift as opposed to trans gauche or gauche, which is at 30.80 ppm. right? So in this study, what they do is then they consider the fraction of the crystalline, lamellar, and amorphous components, and then they assign, all right, so I'm going to have, some fraction of my crystalline components are going to be in the trans-trans chain configuration, same thing for the lamellar, same thing for amorphous. And ultimately, that's going to lead to all of the trans-trans components here. And then I can maybe figure out then how much of each of these components I have. Right, so this is kind of the goal, to kind of identify the different mesophases in this system. So there is a certain amount of like sort of empirical knowledge sort of applied here when they determine the amount of each mesophase, right? So they're creating molecular dynamic models for each particular mesophase and sort of forcing certain kinds of constraints upon them on their models. And then they subsequently run them and they assess to see, right, whether they have how much trans-trans, trans-gauche, and gauche-gauche components they have in each model structure. They then sort of take that and reinsert it into this equation and then determine the populations of the conformers, right? But it's still kind of this combination of simulation and 1D NMR. Okay, and just like a quickly touching upon NMR spin relaxation as applied to organic semiconductors, right? So we know that the mobility of these chains can influence device performance, the density of states, and also electron to phonon coupling effects, right? So just like in other classes of systems, right, we can do temperature-dependent relaxation studies to determine activation energies of the different motion in different alkyl groups in these kinds of systems, right? So this is for P3HT. We see that for the C6 carbon, we tend to have like much faster relaxation at these like lower temperatures, kind of typical for these sort of like CH3. In the case of P3AT, we can also do the same sort of analysis, right? So we can see that at lower temperatures, right, we don't have as many side chain motions. Go higher and higher temperatures, you then see this reflected in your relaxation profile, right? So these are also often paired with MD simulations to support kind of the relaxation analysis. So if you see sort of an increase in relaxivity, why is that? Often that can be coupled also with molecular dynamic simulations. Okay, are we doing on time? Okay, that's fine. So if we want to sort of relate optical response structure, so this multiple quantum MAS study I thought was quite nice, where the goal here was to characterize 3 crystalline polymorphs, so this alpha, gamma, delta aluminum system, right? And so here we have a couple different isomers. So there's a facial isomer that's blue shifted compared to the meridional isomer, right? So this is the meridional isomer, this is the facial isomer. And the difference between the two is one has a much smaller asymmetry parameter, that's the facial isomer, as compared to the meridional isomer, right? So this arises because of the distinct octahedral arrangement of the ligands about the metal. So if we do like a 1D aluminum MAS measurement, right? So here we can already kind of take a look at these and make an assessment of like, okay, which of these polymorphs are related to their meridional isomer versus the facial isomer. So we know the facial isomer has a smaller asymmetry parameter, so then they then associate that with the gamma and delta forms. In the case of this 1D measurement, where we get these sort of second order broadening effects that can limit analysis, right, in a 1D experiment. And this is where running sort of the MQMAS experiment can be helpful, or it allows us to distinguish quadrupolar induced shifts and also isotropic chemical shifts. And then we can maybe learn a little bit more about these sort of more disordered systems, right? So we know this MQMAS correlates the quadrupolar anisotropy axis and the isotropic axis, right? Chemical shift and quadrupolar. And so what we see for the facial isomers is a very narrow sort of distribution here that indicates that we likely have only one site here. So, oh yeah, I just want to call attention to these tilted axes in MQMAS, right? These are the chemical shift axes and quadrupolar induced shift axes, right? So if you have sort of a shift in your line shape here in this MQMAS experiment in this along one of these axes, that's going to indicate sort of multiple quadrupolar shifts. And same thing if you have some shift in this other direction, that indicates sort of multiple chemical shifts. Right, so for the facial isomer, there's a sharp resonance, as I said. And so we have sort of the single set of quadrupolar parameters for both of these. So that's consistent with what we know about the facial isomer. If you then look at the alpha polymorph and the amorphous one, you see these broader resonances. So the reason I'm just showing this, right, is like this is kind of the kind of information that you can get from MQMES, right? We see these broad resonances indicating a large asymmetry parameter, right? So this is kind of consistent with what's known about this, this type of isomer. But more importantly, using MQMES, you then are able to distinguish that there are actually two different classes of alpha polymorphs that contribute to the this isomer, right? Okay. So MQMES, very useful for resolving overlapping isotropic shifts with large quadrupolar anisotropy. Right. Okay, so I just want to touch briefly on how DNP has been used to look at our organic semiconductor materials, right? So since this is a tutorial, right, and we can introduce what DNP actually is here, right? So here in DNP, we rely on spin polarization transfer from biradical system to a glassy matrix. And then via spin diffusion, we can then polarize sort of neighboring systems. In this case, it's a surface of a quantum dot, this example, right? So what's the advantage here, right? In the case where you're not using DNP and you're looking at very low concentration of materials, right? With microwave off, it's very challenging to see the chemical shift and NMR signals of your system. But once you introduce microwaves in the system, you now can more easily see these components, right? So essentially you have microwaves on continuously, and you can transfer polarization from the hydrogen nuclei that have, obtained spin polarization from the electrons, which can then be used to transfer to lower gamma nuclei. Right? So this is just a typical DNP CP mass experiment, right? So if you're working with films, you'll typically grind the films down, and then you'll add your solvent that contains the radicals, right, for your DNP experiment. And so this is actually kind of non-trivial in a way, because there are certain classes of solvents that are used kind of regularly for these classes of materials, but they're not always like a all in solution, right? Sometimes that particular preparation doesn't work well for your system because maybe you have radicals in your system or something like that. So often you have to play with that to get good enhancements. So in these kinds of systems, we're working with much lower temperatures. We have some gyrotron that's supplying the microwaves, and usually we can spin up to around 12 kilohertz with a 3.2 millimeter system, but you can go up to now, I believe, let's see, 65 kilohertz with a 0.7 millimeter, and that might be higher now. But with if there's like a newer DNP probe. So yes, you end up getting broader line shapes. You have to do this at lower temperatures. You kind of have to be smart about the choice of radical and solvent, but there are some that work generally well across the board. You have to have like a high microwave power source and specialized probes, but this boost in sensitivity can be critical for low gamma nuclei and low concentrations, right? So now we're going to do sort of one more sort of case study. Okay, I didn't realize this was going to take us as long. But so let's look at DNP and characterization approach for thin organic films. So, all right, how would so let's say I have this DPP DTT system, right? And I want to establish backbone conformations and molecular stacking arrangements for these films, right? How do I establish a baseline structure if I don't have a crystal structure, right? And so just like what was done in the previous cases, you want to take some model structures, right, of the monomers, right? And this can give you like an idea of, all right, what types of organizations are sort of the lowest in energy compared to sort of the next lowest in energy, and give you a sense of the types of interactions that are at play in the monomers. That stabilize the monomer components, right? So that would be kind of like a first step you can take, right? And so you can use Gaussian NMR crystallography, right? And in this study, in order to then create a model system for the film, Material Studio was then used. So in this case, molecular dynamic simulations are done with classical fields, and you can then obtain some supermolecular structures, right? So here, you can identify the lowest energy candidate structures. Oh, these are quite blurry. Where in this particular study, there were two different kinds of structures that were found, some that were directly stacked on top of each other that were lowest in energy, and some that were slip stacked between the acceptor and donor units here. Okay. So this is kind of what the general approach. Right, so then I can ask, what experiments should I run in order to parameterize the structure, right? If possible, always run experiments on a bulk sample first, give you a baseline. So I'm working with a lot of thin films right now with some of collaborators in the department, and often we're like always running with a bulk sample first. It's a lot easier, and you can get sort of your baseline parameters off right the bat. So right off the bat. You want to do your 1D NMR measurements, CP mass, 1D NMR, how to interpret. You can also take the same approach where you can work with your computational models. If you're just working with 1D, it's helpful to have a computational model. You can calculate the chemical shifts, right? And just with this sort of monomer model alone, you can sort of assess that, okay, one of these structures is more likely than the other. So in this case, from the calculations, a large shift in this H5 component is only present in the case where you have this H bonding occurring between this system here. Okay, and likewise, you can compare the carbon chemical shifts, and this is also in good agreement with the experiment in this study, and this kind of gives you sort of a room to move forward, right? So what further experiments can I run, right? So heck core is kind of the next thing that you might want to run to establish proton-carbon proximities. So in this case, you see that certain carbon residues are correlated to certain hydrogen residues, right? And so based on these models, like these monomer models, it's, in this case, based on the Material Studio models, they found that form 2 was the one that was more consistent with this particular result, experimental result, right? So there's intermolecular interactions between DPP and DTT that given sort of the range of interaction you would expect, it'll only be possible in a slip stack model, right? So the DPP carbons and C1 and C2 in form 1 wouldn't be close enough to support this experimental result, right? So here you then have evidence that this particular structure is the dominant one. So what experiments should I run then in order to further parameterize the structure? So you can run, proton-proton, double quantum, single quantum experiments, and this also establishes proximities between the proton nuclei. In this case, though, you don't necessarily have sort of the same amount of resolution, but the way you read your DQSQ 2D experiments, right? You're sort of seeing where you have sort of these residues that are directly across from one another, and this tells you about the correlation between these different hydrogen nuclei. In this case, we have H5, and then I don't think I have the structure here that shows the which hydrogen this corresponds to. I think this one was the H9. So in this particular case, they didn't have enough, the DQSQ results were not enough to sort of distinguish between form 1 and form 2. Both of them were consistent with the data. And so then in the study, they kind of went back to do sort of refine their calculations. So they took the Material Studio results, and then they ran sort of periodic DFT calculations using CASTEP, which is, free in terms of like academic license. You can get it installed reasonably easily on a cluster. And yeah, you can calculate improved geometries that way. And then when they did that, they saw that, okay, now form 2, based on sort of where the sort of hydrogen nuclei are with respect to one another in this newly calculated structure, and also the chemical shifts, that this is now consistent with experiments. So this is sort of the procedure that's kind of taken. So what about DNP for thin films, right? So often you are kind of stuck with working with a thin film that's now on a glass cover slip, so you might have to crush it and also pack that into the rotor. So you're dealing with a low amount of material. So this is a DNP experiment with one of the the thin film DPP system, right? And so there you see that it kind of matches what was seen in the bulk case. They compare drop cast and spin coated, and all of these preparations, form 2 seemed to be the one that was dominating. They also did DQSQ measurements as well. They're also consistent with what was seen in the bulk, with the exception that there were some hydroxyl groups and water groups as well that one has to pay attention to if you're using glass, because those can be absorbed onto the surface and contribute to sort of some of the broadening in your double quantum, single quantum experiment. Ultimately, they found, right, you can then identify this form 2 is the what the thin film, the drop cast spin coated in bulk all seem to be in. Okay, so I just want to mention a paper that I saw recently from Dimitrios Sakalariou's group. So here they are doing some in situ photoradiation with MAS NMR. And so here they took a optical fiber and they fed it in through a pencil rotor. Right? And so they use this to study photopolymerization on N-butyl acrylate, right? So we're not talking about organic semiconductors here, but I just wanted to draw attention to it because there they saw that you can look the evolution in the solid phase for this type of polymerization under MAS. And they could sort of observe the monomer conversion over time as they extended the UV exposure duration. So this is a nice avenue for setting light-dependent effects in situ with disordered solids. All right, in terms of timing, I think I'm still okay. Just a few more slides here. So, right, so we were talking about characterizing photoactive materials. So we kind of covered some of the approaches that you would take if you're just given like, hey, I want you to figure out what's going on, or I want to figure out like what's going on with this in film. How would I approach it with solid NMR combined with chemical shift calculations, right? So let's now talk a little bit about methods that have been developed to look at doped inorganic lit halide perovskites. And I think I saw Dominic in the audience at some point. So he kind of has published a lot of work in this field. And there's some nice reviews that talk about the methods that can be used to analyze these systems. So like what we were talking about with organic semiconductors, or we're talking about, how these chains are ordered, like how these things are stacked, like all those things play an important role in sort of like charge mobility in those classes of systems. Likewise in perovskites, if you're dealing with inorganic, organic perovskites, you're going to be dealing with some similar issues that you're dealing with in terms of organic semiconductors, or we have these sort of organic systems that can be disordered, ordered. Defects in the inorganic component also play a really important role. You can have a variety of different classes of defects, each of which can also affect the density of states, right? They can affect the absorption, charge carrier lifetime for the reasons mentioned before, where you can have changes in the recombination behavior, right? And so I thought this was kind of a nice paper where they discuss like the classes of defects in perovskite halides, and directly connect it to observations in devices. So as we know, right, defects in both in organic semiconductors and perovskites, they can vary according to preparation conditions. And, once again, looking at local short range order, changes in anisotropy, local magnetic environment due to doping or introduction of defects can be very helpful in terms of assessing how the structure is changing, right? And so one thing I'm not going to talk about today, I was initially going to try to talk about it, but I think it was just a lot of content. Electrically detected magnetic resonance, I think hasn't really, I feel like I haven't seen as many publications on this. Like there's a lot of cool stuff coming out of Christoph Boehm's lab, where they've been looking at defects in devices, and you can look at changes in the current of a solar cell, for example, upon microwave radiation. These all give you an indication, like a direct indication of the defects that are directly pertinent to device function. I think it's something that I'm definitely interested in sort of keeping an eye on. I just wanted to, if you haven't heard of it before, I just wanted to mention it, and you can kind of take a look at this paper here if you want to learn a little more. So there's a really nice review, right, from Dominique and Lyndon, Claire, also Sam. where they talk about NMR spectroscopy probes for microstructure, right, and dynamics. So essentially, right, we can ask the question again, okay, some of my animations didn't work here. What kind of experiments are typically run, right? We want to do 1D to identify cation incorporation, you get through changes in chemical shift. You can also use 1D NMR to identify structural changes due to passivation. I think one thing I like about sort of combining some of the solid state NMR material science, like sometimes there are kind of fairly straightforward experiments you can do when you talk with material scientists and you're like, well, and it answers a very important question, right? Right, you can also do 2D proton spin diffusion measurements to obtain atomic level proximities, paramagnetic relaxation to characterize magnitude of incorporation of these different molecules. And you can also do cation dynamics with deuterium NMR. And so a lot of this is described in this work if you're interested in it. Oops. Okay, so what was I saying here? Right, so here's just an example of, when you incorporate manganese into cesium lead chloride, you can see changes in the relaxation behavior, right? Changes in T1 will scale according to how much paramagnetic centers you put in there. How do you prepare these kinds of systems? So a lot of these systems can just be prepared with mechanosynthesis. You mix in stoichiometric amounts. You mill for 30 minutes. And you can then anneal them, and you get reasonably good structures that have like a single phase XRD results. You can use this for hybrid perovskites as well as inorganic perovskites. Right, so there's a study also that came out in JAX really recently. I don't have the year there. I think it was last year, where there were a series of lanthanides doped in perovskites. And it was found that you can identify certain motifs upon incorporation of different classes of lanthanides, right? You get a decreasing, there are certain kinds of motifs in the perovskite structure that rise across this, period here. So they find that decreasing ionic radius tunes the tolerance factor, and this leads to more octahedral tilt. So I was drawing this little arrow here to indicate. They also see new resonances in cesium lead chloride, indicative of new defect sites, which I think one thing my lab is interested in right now is kind of further analyzing some of these classes of defects. And also, in the case, you can have different cases where either structural effects dominate or paramagnetic effects dominate, but I won't necessarily do this description as much justice. I wanted to just draw attention to this, to the audience, to this paper. Right. And you can also have a case where paramagnetic effects dominate, and then you see changes arise in the structure in the spectrum due to pseudo contact shifts. And so lastly, just another example here, looking at hybrid organic and inorganic systems. You can look at once again systems with organic components, and here we're once again thinking about pi stacking or sort of like slip stacking. In this study, once again, the MD simulations are done, DFT chemical shift predictions are done for several different model structures. And it was found that only in the phase segregated structure that they designed did it match up well enough with their experiments, right, within the RMSE levels, tolerance levels, right? So in this case, they showed using sort of a series of 1D NMR, 2D NMR experiments, like we had talked about the rest of this presentation. They were able to identify that in this class of systems, they have nanoscale segregation. Okay, so that's essentially, what I've covered, like a couple different types of case studies on analyzing this class of materials, and a lot of them do rely somewhat heavily on chemical shift calculation. So I think it's important if you are in this field or entering this field to gain a decent understanding on DFT calculations using Gaussian. And maybe if you're not familiar with MD dynamics, getting a collaborator to sort of work with. So this is my group. We're working on a variety of different things like spin polarization induced optically, and as well we started looking a little more at some materials, both perovskites and organic semiconductors. All right, so thank you for your attention.
All right, that was a really informative and really rich in content,
Yeah,
comprehensive overview. of studying this class of materials using solid state NMR, a lot of techniques. So I really enjoyed your talk. And so for the audiences, if you have any questions to Claudia, please feel free to type them in the uh, in the Q&A, or you can raise your hand if you have that function. Um, so I want to just make a quick announcement for the next Global NMR speaker. Will be Professor Chad Reinstra, scheduled on the Tuesday, March 11th in 2 weeks. He will be talking about some cool stuff. The title is still to be announced, so stay tuned for that. So I guess I would like to start with one question. You mentioned you emphasized that the DFT calculation to have some understanding of the chemical shifts and compare that with the NMR spectroscopic features are really important, and I really agree with that. So in practice, the estimation, let me think how high I want to ask this question. Uh, Whenever we're dealing with the ensemble behavior, then different populations, for example, in different domains, start to be really become complicated, and how to sort of find a balance to avoid overfitting, but also provide the
Yeah, I think one of the examples I gave, I think I personally am not clear. Like I think that you have to be very clear on the constraints and be very specific on like this is very probable. This is how, this is true. But like I feel like in especially in that case with the mesophases, I think that may have been a case of overfitting. But it's yeah. So honestly, I would just say that you just have to be very sure about the constraints. But it's correct to be cautious in those cases where you don't have a good sense of the constraints. I'm kind of like repeating myself here, but yeah, I think it's safe. It's correct to be a little cautious in those cases. But I'm still also gaining a bit more experience here in these classes of systems myself. So yeah.
Yeah, I guess I fully agree with that. Sort of follow up on that. Do you think is it I'm personally not a solid state NMR spectroscopist studying this type of materials. Do you think it's easy enough to prepare some sort of standards in terms of the samples, different compositions of the sort of materials, so that we know they would pack one way or the other, and then see whether a unknown sample or the sample of interest sort of fits in some of the calibration curve.
Um, I guess like comparing the sample to sample, if there might be a little bit like comparing apples and oranges if you have a different class of organic semiconductor. And I don't think that the material science is at the point where you can direct it completely. Like, I think maybe for certain types of systems, yes, where you can direct it to one particular type of well, okay, I guess I am saying like, yes, you can probably direct it to one particular type of polymorph, but in terms of like all of sort of the different mesophase components, right? Sort of slightly, we have these different like crystalline islands versus like semi-crystalline. I don't think you can necessarily just isolate just the ordered, like create a sample that just has the ordered components, particularly in organic semiconductors where you have a lot of positional disorder along sort of like the pi stacking. You can have sort of like quite a distribution. I don't know how well you can order that. I'm also not, a pure material scientist, right? I'm more of a spin physics person, but
Right.
that's understanding. Though someone in the audience might have more experience as well in that.
Yeah, so we do have one question in the Q&A channel. Vinod Kumar Avalos is asking how versatile is a solid state NMR compared to a cost-effective characterization technique. such as the Raman spectroscopy in characterizing the photoactive materials?
Yeah, so I mean, I guess like the advantage of solid state NMR is you do get this sort of like local atomic structure, right? You can really set nice constraints on distances, especially for these kinds of mixed amorphous semicrystalline materials. So my understanding is, yeah, like with Raman spectroscopy, you're still looking at kind of like a broad sort of, you're looking at sort of a more periodic system, like periodic components. But I would say, like, yeah, with solid state NMR, you do get this sort of additional advantage of these like very local distance constraints. And also you can do these sort of multi-dimensional experiments as well, which I guess maybe with advanced Raman spectroscopy you might be able to do.
Yep, yep. Great.
Um,
Uh, the other question from Christopher Klug is asking any idea why the enhancement for the dropcast film is 3 times larger than for the spin-coated film?
so I know like, but the dropcast film was definitely thicker. That's the only thing I can say is like when they dropcast it, they were dealing with more of a micron thick layer before they scraped it off, before they crushed it, as opposed to the spin coated film where they had the 400 nanometer layer. So that could have something to do with like how well it's sort of incorporating into the sample. You just have like, yeah,
Yeah. Also,
grinding.
do you think during these different sample preparation processes, there would be indication of self-assembly type of phenomena?
Yeah, so you're saying, right, like when you crush it, how much is that actually changing the structure? Yeah. Um, yeah, it's a valid concern. But I mean, I think there's also there's like the comparison with the bulk powder, the thin film, which, it's kind of a way to kind of look at the sort of some consistency. And it's not, I think there are cases where sometimes the film can, as we saw in one of these sorry, as we saw in one of these case studies, there was like a little bit more order in one of the films than the powder. So I don't know. I guess there could be some differences, but yeah, I'm kind of giving you a wishy-washy answer here, but I think you should probably be reasonably cautious. But I don't know. I don't know how much the grinding really perturbs the structure that much. Yeah.
Um, I also want to ask, could you provide some general comments about studying this type of a class of materials when usually they kind of perform in either in the bulk configuration or film configuration where the surface effect seems to be relatively small versus when we grind them and pack into the solid state NMR rotor, we seems have increased the surface to volume ratio, and probably that will, let's say, prioritize the NMR categorization, focus on those, let's say, more disordered surface.
So I
So
guess
just
like when
ideas.
I guess when you're grinding these systems, at least I know for, just mortar and pestle, I believe like in Lyndon's lab at some point, someone actually did look at the SEM of like particle sizes as you ground for like longer, and you weren't really getting anything much smaller than like a few microns. And so I'm not sure if then the surface would really come into play as much there. Yeah.
We got another question
Yeah.
from
Yeah.
Aaron Rossini. Well, it's more like a comment. The surface area of micro-sized particles is negligible compared to the bulk.
Yeah.
So thank you for that information.
Yeah.
Yeah,
That's consistent. Yeah.
let's wait for a couple more minutes to a couple more seconds to see if there are other questions.
I guess maybe I'll also comment on like sort of I kind of wandered from like optically detected magnetic resonance to like looking at these classes of materials in terms of my career. And it's like a kind of got
Right, right.
interested in like sort of optically excited systems. And this sort of was sort of a natural sort of merging of collaborations with some people in my department in terms of looking at these types of structures. So yeah. Anyway, if anyone that's known me for a while is wondering what what I'm doing
Right,
right
right.
now, these sorts of
So are you
things.
more thinking of taking the approach of using sort of optically detected magnetic resonance sensors to look at the magnetic properties of those materials, or sort of use it as a way to do hyperpolarization?
Yeah, I've been thinking a lot more about like hyperpolarization and like more about relative energy levels of like different donor acceptor systems as well. And how that can be considered also for ODMR. So it's kind of, yeah. Obviously it gets more complicated when you have these sort of more device structures as opposed to a molecule in the glass. But yeah, this is sort of how
Yeah,
I've
yeah.
a little bit more in these classes of materials.
So actually, one thing that really sort of impressed me is the example you gave when they shine the light through inside the rotor and then study the photocatalysis activities in
Yeah,
situ. I found that pretty impressive, especially thinking from an instrumentation perspective.
yeah, Demetrius has had like a nice setup there, and we have a setup going right now. But anyway, it's I'll talk about it once we have some more stuff to talk about on that
Yeah,
front. But
or
yeah, it's definitely something my group is interested in right now and completing, yeah, as well. So.